All right, so percent composition is hydrated crystals. Monday morning, nobody's in the mood, but we're going to do it anyway, okay? Now, you calculate this percentage to be what? This is 1 mole. 1 mole of copper 2 sulfate pentahydrate. This is the equation. This is showing you exactly what's happening here. This is showing you exactly what's happening here. Is 1 mole of copper 2 sulfate pentahydrate, that's what the pent refers to as that 5, is heated, and the copper 2 sulfate separates from the water molecules, right? The kinetic energy increases to the point where the water molecules actually are literally shaken off the crystal, and they evaporate away, okay? So you're left, if you've done this perfectly, and which is impossible, you're left with nothing but copper 2 sulfate. Anhydrous or dehydrated copper 2 sulfate. Everybody got the picture? Now, when you're talking about 1 mole, okay, then the masses come out to this. 1 mole of copper 2 sulfate pentahydrate has a mass of 249.72 grams. 90.10 grams is water, and 159.62 grams is copper 2 sulfate, right? What are the percentages? .08% here, and so that would leave what? 63.92% here, okay? Everybody got that? This is 100%. Yes? Okay. Now, this mass right here equates to this mass, okay? This is the total mass that you have. It is not a complete mole. It's about 1/100 of a mole. It's slightly over 1/100 of a mole, right? Everybody see that? Ms. Farnham? Yes? But the percentages are the same. Okay? So you know, already, you know, as soon as you have this mass right here, and you see this mass of anhydrous crystals left over, you already know the answer to your lab. Right? You can calculate this percentage right here, compare it to that percentage right there, and you know the answer to your lab already. Does anybody not see that? Does anybody see that? Okay? So all you're doing on the entire rest of the lab is demonstrating what you already know. Got it? Yes? I'm not getting the feeling that we're following along here. Do you understand, Miss Cassie, what I'm saying? Ms. Farnham, you're putting lipstick on. You got it? You understand what we're talking about? Okay? All right, so we go to the calculations here, and this first step right here under calculations is asking you to calculate the formula mass. It's just you demonstrating to me that you know where that 159.62 came from. It came from the mass of copper, 1 mole of copper, 1 mole of sulfur, 4 moles of oxygen, 159.62. The total mass is going to be the mass of the formula mass of copper 2 sulfate plus the mass of 5 water molecules. That's where the 249 came from. Everybody understands that, right? Yes? Okay, number 3 is asking you to calculate the mass of water removed. Okay, very straightforward. I know it can be confusing, but it's very straightforward. So what you're going to do then is you're going to take number 3 here was the total mass. Okay. Number 6 down here on your data table was the mass of the anhydrous crystals, or the dehydrated crystals, right? The difference between the dehydrated crystals and the hydrated crystals is the mass of the water, okay? And that's what this is right here. This is your total mass. This is the sample you used. This is what you had left when you said you ran all the water off of it. So the difference between those two masses is the mass of the water. Does everybody understand? That's the mass of the water, okay? Now, you could at this stage right here calculate percentage if you wanted to, but in this particular procedure, we're just asking you to hold on a second. We're going to get to that in a second, okay? So now it says take this mass of water and convert it to moles of water. Everybody understands? There's no problem there, Mr. Gradle, right? You're going to take the mass of water, and you're going to multiply it by 1 mole of water per 1802 grams per mole, right, for water. So essentially what you're doing is you're canceling this unit here, okay, and you're converting it to moles. So you divide the 0.97 by 1802, and you come up with 0.053829, whatever. I got extra significant figures in there deliberately, because I'm trying to show you that I don't want to round every single step. I don't want to round and round and round and round and round, okay? I'll take my answers and round one last time. Got it, Mr. Hubbard? Okay? So there's moles of water. All right, now, we come over here to step number 5, and it says now you take the mass of the dehydrated or the anhydrous crystals and convert that to moles. We established at the outset that 1 mole of copper 2 sulfate has a mass of 159.62 grams, okay? Again, all we're doing is changing units, although I didn't put the unit there. We're changing the units, okay? We're going from grams to moles. So we divide by the molar mass of copper 2 sulfate. It gives us 0.01096 moles of copper 2 sulfate. Everybody with me? Still with me? So now, this goes back to our entire chapter 7, and we realize that, you know, all the way back to John Dalton in the 1800s, atoms don't bond in fractions. They bond in whole numbers. And luckily for us, small whole numbers, okay? So all we have to do is take this ratio of moles of copper 2 sulfate to moles of water and convert it to whole numbers, right? And that will give us our experimental formula. That will tell us what the formula is based on our data. And we hope, we already know the real formula is 1 to 5. We hope that our data will give us that, okay? So, this is moles of copper 2 sulfate. This is moles of water we just calculated, right? Now we're going to divide by the smallest number. That will obviously give us a 1 here and almost 5, a 4.9115 moles here. Well, we realize that this is the closest whole number is 5. We realize that, you know, this is a lab. We're using a balance that only takes us to 100th of a gram. We use a fairly small sample size. We are not likely to get much closer to a whole number than that, okay? This is where you use judgment. This is where you have to have your data here, okay? This is where you're showing whoever's looking at your work what you're basing your decision on, okay? So, we're saying that this 1 to 4.95 is essentially a 1 to 5 ratio, which says that our formula unit, our formula of copper 2 sulfate, the hydrated crystal, is 1 mole of copper 2 sulfate to 5 moles of water, okay? So our experimental formula matches the actual formula. Yours may not. Many people come up with 1 to 4. Why would you come up with 1 less mole of water? What would be the usual cause for that? Go ahead. Didn't drive enough water off, okay? You quit too soon. You thought you had driven it all off, but you didn't. There was still water in there. So then when you calculate the mass of water that you drove off, it would be low. Okay, and if it's just low enough, it'll push you from 5 to 4 in your calculation, okay? And so if that's what your data tells you, the way you get an A on the lab is you report that incorrect formula. Because what you're doing here, and this is the hardest thing for new students, new science students to understand, is you are interpreting the data. That is what you're doing here, okay? You're not here to report that the formula for copper 2 sulfate pentahydrate is 1 mole of copper 2 sulfate to 5 waters. That's in the formula name. That's given to us, right? You're here to interpret your data and show that you can correctly interpret your data. Do you follow what I'm saying? And that's the hardest thing. It's the biggest step for many students to pick up on their, you know, when they first start doing labs that actually collect data. And in biology, you know, your last science class, you're really, most of the time what you're doing there is you're making observations, okay? You're not really you know, manipulating data, calculating with data, okay? So now here on your percent error, What I'm asking you to do is take your masses and compare your masses, okay? You could do it with percentages, but I'm asking you to do it with masses, okay? So you take the 36.08 that we calculated in the very beginning and you multiply that by your sample size. If it was 2, then your correct mass would have been what? 0.7218, right? 0.7218. But mine was my sample data here is 2.72. So the correct mass, if I were perfect on here, would have been 0.9813, whatever, right? Okay. But the mass that I actually measured was 0.97. So my theoretical value is here when I take the actual percentage, multiply it by my sample. Then if everything went perfectly, I would have had 0.98 grams of water driven off. Okay, that's my theoretical value, or sometimes you hear it called accepted value. Okay. My experimental value is what I actually measured, which was 0.97. Right? And I have these marks here. I put these marks here on experimental error. You should get in the habit of writing this equation or writing this formula for experimental error, percent error, writing that down every time before you use it. It helps you remember it. It helps you collect your thoughts so you know what you're doing. But you write these absolute value marks. That way, if your experimental value is larger than your theoretical value, you don't have to worry about having a negative percent error. Okay? So what we're going to do then is our accepted value is 0.98. Our experimental value is 0.97. So we subtract the 0.97 from the 98 and divide by the 0.98. Multiply by 100, and that gives us our percent. So here in this sample data case, we're very close. 1.159. However, I have to reduce it to 2 significant figures. Why? Ms. Cook, why? Because my mass is only in 2 significant figures, right? Because the balance only goes to hundredths of a gram. So when we report our error here, we're limited by our equipment, which is always the case. We're limited by the precision of our balance. Okay? Now we're going to do a quiz, a lab quiz here. And the exact same thing, it's going to be the exact same procedure here, except in the data table, I'm going to give you the data. Okay? And everybody is going to try to calculate the percent error in the data that's given to you. This will stay the same. Okay? And furthermore, you can use your lab to calculate your data. I mean, to calculate your results and your percent error in the lab quiz. Okie dokie? It doesn't get any easier than that.